Hi students, today we are going to discuss the method of production of induced EMF by changing the area of the coil, and the EMF induced in the coil is now called by the name what? Motional EMF. Why? Because due to the motion of a conductor inside a magnetic field. Okay, now for this I have considered a rectangular loop. Okay, the portion PQ or S, this is a rectangular loop, out of which the portion PQ whose length is L is movable. Okay, it is movable. It is look here. So this is a rectangular loop. It has three sides. Can you see the three sides completed? The fourth side is incomplete. So I take a separate portion, the fourth side, a separate portion, and I am going to place like this. Can you see that the area of the rectangle is equal to its length into breadth? Okay. Now this is the portion PQ. The remaining portion is incomplete rectangle. When I keep the portion PQ, it closes the rectangle and then it is moved. It is moved inside the magnetic field. So this portion PQ is able to slide or move perpendicular to a magnetic field B. So what type of magnetic field I have considered here is perpendicular to the plane of this board. This X marks represent that each magnetic line of force is passing perpendicular to the board like this. So it is a uniform magnetic field which is perpendicular and passing inwards. Okay. So outside is the north pole and inside the board is the south pole. So inside such transverse or perpendicular magnetic field, I place a conductor, okay, incomplete rectangle, and I keep the portion PQ which is able to move perpendicular to the field from the portion PQ to a new portion P dash Q dash. So now can you imagine that when I move the fourth portion PQ perpendicular to the magnetic field, does it cut the lines or not? It cuts the magnetic lines of force like this. So that now when I place the portion PQ at the new portion P dash Q dash, the area has now decreased. So initially it was having a larger area. This larger area was associated with the magnetic flux. When I move this portion inward, only a smaller closed loop you can see. Only a smaller portion is associated with the magnetic field. So the remaining portion, that much area of the loop has now decreased. So due to the change in the area of the loop, now how much flux change will take place? That is what we are going to discuss. So once again I am repeating, my dear students, a rectangular portion, incomplete portion is kept perpendicular to a vertical magnetic field, and the fourth portion PQ is moved towards the left. So I am going to move this portion PQ towards the left hand side with a constant velocity V for a time dt, a small fractional time dt. So when this velocity is constant, okay, and it is moved for a time dt, then how much will be the distance from Q to Q dash? So this distance Q to Q dash, this distance must be equal to V into dt. Okay. So when the portion PQ has reached the portion P dash Q dash, now the remaining area of the loop associated with the magnetic flux has now decreased, is it not? By how much means? By a small portion PQ Q dash P dash. So now you have to remember that V is the magnitude of velocity which is constant. So I can also write a constant speed, okay, or constant velocity, and dt is the time taken during which the portion PQ has moved towards the left. Therefore the distance moved, okay, the distance moved is equal to V into dt. This much distance it has moved. Also, how much area is now reduced? So, decrease in area. The decrease in area, which is also called a change in area. Okay, change in area. dA. dA is the change in area, and that is equal to the area P, Q, Q dash, P dash. This small area. Its length is L, and the width it has moved is equal to V into dt. So how much is the decrease in area? So this decrease in area dA must be equal to L into V into dt. So this is our equation number 1. Are you understanding the first equation? Yes. When PQ is moved towards the left with a velocity V, constant velocity V for a time dt, okay, it moves through a distance V into dt, due to which the area of the rectangular loop changes, that is decreases by how much? By quantity equal to this small area P, Q, Q dash, P dash, that is equal to length L into the width V into dt. Therefore, what is the change in magnetic flux? The change in magnetic flux is given by d phi. D phi is the change in the magnetic flux. So this is equal to the magnitude of the field, magnetic field B into dA, B into change in area dA. So this is now equal to B into change in area dA. What can be substituted from equation 1? L, V, D, T. This is equation 2. Okay. Now this is the change in the magnetic flux. Now this term dt, that is the time during which the flux has changed. So rate of change of magnetic flux d phi by dt. This dt is brought to the denominator on the left hand side. What will be the remaining term? That is B into L into V, and this is denoted with a symbol epsilon, and this only is called as motional EMF. Understand that? So derive an expression for the motional EMF associated with the rectangular coil. It's a 3-mark question. So for 3 marks you have to write up to this. So I can write therefore the motional EMF is equal to what? BLV, and this is the equation 3. Epsilon is equal to BLV. Now this coil is made up of copper or aluminum or some metal only. Is it not any metal? So it will have some resistance R. So what will be the current which is induced? Because the portion PQ is moved inside a magnetic field, the flux is changing, due to which an EMF is induced. This induced EMF only is getting a motional EMF because of the motion of the conductor has produced this induced EMF. So if you divide this induced EMF by the resistance of the conductor, you will get an expression for the induced current, and the direction of the induced current, that I, is always opposite to the direction of motion of the conductor in accordance with the Lenz's law. So when the conductor PQ is moved in the left hand side, then the induced current will be in the right hand side, clockwise direction. The current will be flowing in the clockwise direction. Understand? So the induced current is now given by I equal to E by R, where epsilon by R, where epsilon is what? The induced EMF. So this is now equal to BLV divided by R. So this is equation 4. So equation 3 is the induced EMF, and equation 4 is what? The induced current. So sometimes the derivation may be up to equation 4 also. But now sometimes if it is asked as a long answer question or essay type question means here, how do you prove the conservation of energy? Energy conservation. What is meant by energy conservation here is, we are moving the portion PQ towards the left hand side. So externally we are doing some work. Is it not? That is equivalent to the mechanical energy which I have spent. So the mechanical energy spent on this portion PQ has moved it to a new position P dash Q dash. And in turn, this will be converted into electrical energy. Understand? Electrical energy, and that will try to push it in the right hand side, so that the energy is being conserved. That is, we are going to prove that the mechanical energy spent is equal to the electrical energy produced in the closed loop. So the next, if it is extended, means the next title will be what? Energy conservation. So for energy conservation, now first we will find out what will be the force acting on this current carrying conductor. Now this current I is flowing in the downward direction. Induced current is flowing in the downward direction. Understand? So this I into L is called the current element now. I into L is called the current element, and that is in the downward direction. Now it is a current carrying conductor placed inside a magnetic field. So what will happen when a current carrying conductor is placed inside a magnetic field? It will experience a motor force. That motor force is given by Fleming's left hand rule. Is it not? So you can see here the field forefinger is inward. Okay, and the current given by what? The middle finger. The middle finger is in the downward direction. You see that two fingers, it will be like this. These two fingers are like this, one into the bone and one is downward. See the thumb in which direction? The thumb is pointing towards the right hand side. Is it not? Thumb is pointing towards the right. So in this direction outwards, there will be a force due to the magnetic field. So this is the force due to the magnetic field. But in which direction we are pushing the portion PQ is towards the left hand side. So in this direction, what will be the force? A constant force, I told you, that is called as applied force. We are applying a force towards the left hand side, but the magnetic force is towards the right hand side. Understand? So the magnitude of these two forces must be equal. Okay. So I will write here the magnitude of the applied force is equal to the magnitude of the magnetic force. Okay, so in modulus, if I write means a vector symbol I can use, otherwise without vector symbol also I can write. So first of all I will write this is a modulus of these two forces are equal, and this is F is equal to IL, okay, cross B, IL vector cross product B vector. Therefore, F applied magnitude is equal to FB magnitude, that is equal to ILB into sine 90. So that is equal to ILB. So in this case, IL vector and B vector are perpendicular to each other. Is it not? I said that this is the middle finger downwards, IL vector, and the forefinger, that is the field vector, they are perpendicular to each other. Therefore, the force will be perpendicular to the plane containing the other two vectors. So, ILB. So, this is our equation 5. So, the magnitude of these two forces will be the same. Now, we are applying a force on the portion PQ, that is called the applied force. What for? To move the conductor PQ towards the left hand side with a constant velocity V. Are we doing work or not? We are doing work. And work done divided by time only is called as what? Energy divided by time, that is called as power. Is it not? So, I will write applied power. The power applied on the conductor P is equal to the dot product of the applied force vector and the velocity vector. We are applying a constant force. We are applying a force so that the conductor moves with a constant velocity. So the dot product of the applied force and the velocity, you can see here velocity as well as the applied force both are in the same direction, is it not? So what is the angle between these two vectors? 0. So this is a dot product. So this is equal to F into V into cos 0. Therefore power P is equal to what? F into V. F into V, applied force. So this is the applied force. So instead of applied force, what can I substitute here? Applied force is what? ILB. Is it not? So I will write applied force is equal to what? I into L into B. Into velocity V is there, is it not? Into velocity V. So now this current I. What is the expression for the induced current I? Already we have written BLV divided by R. I am going to substitute this equation 4 instead of I here. Is it not? Therefore, power P is now equal to BLV divided by R. This is instead of current I. Look at the equation 4. Current I is BLV by R. I have substituted for current I here. What is the remaining? One more BLV term is there, is it not? So one more BLV term is there. Therefore, P is now equal to B square L square V square divided by R. And this is our equation 6. Step by step, you will have to write and practice. Okay. So this is the applied power. But we have already studied that electric power P is also equal to I square into R, voltage into current. Is it not? So I will write now also power P is equal to I square into R. Is it right? So I square, in place of I, what shall I write now? BLV by R the whole square. Understand? So now this is equal to BLV by R the whole square. From where I have substituted is from equation 4. So I square into R. So into R. So this is equal to B square L square B square divided by R square into R. So this power 2 and R get cancelled. Therefore, we get P is equal to B square L square B square divided by R, and this is equation 7. Okay. So here the applied power from the dot product of applied force and velocity, we have got equation 6. This is the general expression. Okay. So we get equation 6 and 7 both are one and the same. So this is mechanical power. Applied power is mechanical power, and this equation 7 gives what? Electrical power. Is it not? So the applied power and this electrical power both are one and the same. This is because the mechanical energy spent for the time dt has been converted into electrical energy for the same time dt. So energy per time only is called as the power, is it not? So totally what is happening here? Electrical energy is produced at the expenditure of mechanical energy. So mechanical energy is spent and is getting converted into electrical energy. Is converted into electrical energy. This energy per unit time only is called as the power, is it not? So mechanical energy is converted into electrical energy. And suppose if that electrical energy produced is not consumed, if it is not taken out, then it will also be converted into equal amount of what energy? Heat energy. Okay. So this is in accordance with the law of conservation of energy. So the total energy remains constant. So, my dear students, if fully they asked how the question will be asked in the exam, explain motional EMF induced in a conductor, okay, placed in a uniform magnetic field. Hence, prove the law of conservation of energy. If they ask a lengthy question, it is for 5 marks. You will have to write up to this. Very simple actually. You will have to write and practice systematically. So, first we have to consider a rectangular loop of the fourth side incomplete. When the incomplete side is made complete and moved, okay, the area of the loop which is linked with the magnetic flux changes by how much? By dA. So, we started with the first step, what? The change in area, decrease in area. Then the change in magnetic flux, d phi is what? B into dA. Understood? And then the rate of change of magnetic flux, that is what? Induced EMF. Then induced EMF divided by the resistance of the conductor. It will give you what? The expression for the induced current. Up to this one sequence. At least up to this everyone must be thorough. After this, how to prove the energy conservation here is based on this equation. So we are applying a force on the conductor in one direction and an opposing force is due to the induced current in the opposite direction. So that the magnitude of these two forces will be what? IL into B. And then the power is the power, applied mechanical power to move the conductor is what? A dot product of applied force into velocity. So from there we got an expression 6. Then also from the definition of electric power, P is what? I square into R, we get equation 7. Equating these two, we have proved that the mechanical power is equal to what? The electrical power. Therefore, the mechanical energy spent to move the conductor must be equal to the electrical energy generated in the conductor due to the motional EMF. I hope you must have understood well. Fine.